Welcome to this video, the third part of direct displacement based design. Here we shall take up a numerical problem and solve it with the Excel sheet so that it is clear how to implement this in real practice. So question is given to us. Find the design forces at each floor level for the 10-story building, the plan of which is shown below. The ground story height is 4 meter and other story height is 3.5 meter. The seismic weight in floors is 11 kilonewton per square meter and that in roof is 6 kilonewton per square meter. The grade of rebar steel is Fe500 and the overall depth of all beams is 600 millimeter. Design depth is 2.2%. The building is to be designed at 0.42 G level of EC8 code, that is Euro code. So here the building plan is given. The long directional beams are 6 meter and short directional beams are 5 meter. We shall show calculation for along the long directions only, and the remaining thing you can do yourself. First calculate the weight in the floor. The length is 18 meter and breadth is 10 meter. So 18 into 10 into load intensity 11 kilonewton per square meter, 1980 kilonewton. Convert it to mass, multiply this by 1000 and divide it by 9.81 and you get the mass in kg. For roof level, the size is same and the load intensity is 6 kilonewton per square meter. So I get 1080 kilonewton and corresponding mass is 110091 kg. Now we shall open up the Excel sheet. Yes, so this is the Excel sheet where we have taken up the given data. Theta D 2.2%, that is 0.022. Height of ground story is 4. Height of other story 3.5. Yield strength of steel 500. Modulus elasticity of steel is 2 into 10 to the power 5 megapascal. HB, the depth of beam is 0.6 meter. LB, the length of beam is 6 meter along the long direction. And we put these values in the ground level. I have 4 meters, so I put 4 here. And other story heights I'll calculate like this, equal to 4 plus this 3.5. And since it is a constant value, I want to put dollar here. So this is this, and I can drag it to get the other heights. So we have the top floor at the top, 10th is the roof level and 1 is the first floor level. So these are the weights. Now if I take sum of all this, then the final height is 35.5. So height of the building is this. So this equal to this one. 35.5 is the total height of the building. Let us find out the strain in the steel. So it is equal to the Fy divided by PS, this one. So this is the strain in the steel. Now we need to calculate phi I. Phi I formula is given here. For we are taking Pettigrew and Priestley expression. So if n greater than 4, then phi I equal to 4 by 3 hi by h, 1 minus 0.25 hi by h. So let us put this formula. Phi I equal to 4 by 3 into hi by h. So hi is this height divided by the total height, this one. Since this is constant, we have to put $10 here. So in the formula, this part we have done, then 1 minus this thing we have to do here. So put a bracket, 1 minus 0.25 star hi by h. So we again multiply this hi divided by this overall height, and this is constant. There is some problem in the formula. What is the problem? 4 by 3, alright. C9 by this is alright. Oh, here star is not given. So we need to put multiplication sign here, which is missing. Still there is some problem. What is this? So this has become wrongly come here. It should be star. Yes. In a mode shape, at the top level generally it is 1. So if you apply this formula over the other floors, you get the mode shape coefficients for all other floors. Now delta C, you have to, the critical story you have to identify. Obviously the tallest story height is the ground story, 4 meter. So this is my critical story value. This is critical story. So this 0.146 is the phi C, the value of phi at the critical story. Now delta C you have to calculate. Let us calculate delta C here. Delta C equal to delta D into HSC. Delta D is this, star HSC is the critical story height, which is 4 meter. So this is the delta C value. Delta C theta D into HSC. HSC critical story height. Now delta I is given by phi I into delta C by phi C. So I can write down the expression of delta I here equal to phi I, which is here, star delta C, which is here. So this constant, you have to use dollar, divided by phi C. Phi C is this, we have seen 0.146, and this is constant. So this is your delta I, and now we'll apply it over the other stories, and these are the values of the displacement profile delta I. So mi delta I is simply product of these two columns, mi column. These masses from the previous slide I have taken up here. At the roof level, this and other level, it is same as 2021, 834, etc. So this star, mi star delta I. So this one. This is the product. We don't need perhaps all the decimals, so we can reduce the decimals. Even no decimal is required perhaps because figures are big figures. Then apply this formula over the other floors. So these are your the mi delta I equal to your mi delta I square. You have to take star delta I. So this is applied over the whole building. Mi delta I, then mi delta I hi. So this is equal to this mi delta I column star height column, which is here, and apply it over the entire building. Okay, now we need to find the summation of certain columns for the mi delta I square, mi delta I, mi delta I hi, etc. So here you put sum equal to sum yes, and I can copy and paste this to other column. Yes, so these are the summation values. Let us boldface it and increase the size to understand, see it nicely. Now we have to find out the delta D. So delta D is summation of mi delta I square divided by summation of mi delta I. So it is very easy to find now, equal to summation of mi delta I square, which is this, divided by summation of mi delta I, which is this. So this is in meter. We don't require perhaps so many decimals. this is the design displacement delta D. Now M equal to mi delta I by delta D, summation mi delta I by delta D. So this value divided by this delta D value we have calculated. So this gives you the effective mass. Then HE equal to mi delta I HI divided by mi summation mi delta I. So equal to this last column divided by mi delta I summation is this one. So this is the HE, the effective height of the building. Effective height of the building will be certainly lower than real height. Real height is 35.5 meter. Effective height, which is the height of the equivalent single degree of freedom system, which is lower, so it is 23.323 meter. Now we find the yield rotation of the frame, which is 0.5 epsilon y LB by HB. All these parameters we have written here. So this is equal to 0.5 star epsilon y, which is written here, star LV, length of beam 6 meter, divided by depth of the beam, which is 0.6 meter. So this is your yield rotation of the frame in radian. The value is small because the yield rotation will be a very small value. Then we need to find the yield displacement, which is this yield rotation value into effective height. So this is very simple to calculate, equal to this value star HE. So this is your delta Y in meter. Now the ductility mu delta D by delta Y. So equal to delta D, we have found this value, divided by delta Y is this value. Yes. So it is 1.47. The ductility should be always more than 1, otherwise you have some problem in your computation or in the system. Because ductility 1 means it is elastic, it should be more than 1. Now we find the equivalent damping, which is 5 plus this formula. So we calculate here, equal to 5 plus 120 star. We require another parenthesis 1 minus 1 divided by SQRT square root of mu. This is the mu value. So this part we have done. So this is bracket closed, divided by pi. I think it is alright. Some problem. What is the problem? I plus 120 star bracket stars 1 minus 1 divided by SQRT of that mu value. Then we have closed the bracket. SQRT bracket is closed and this bracket is closed. I think another bracket required or what? This is closed here. This is this. Another bracket required here, I think. Yes. So the value of the equivalent damping is equal to 11.7%. This is alright. This is a practical value. It will be of the order of this. Now we'll go to next sheet of the Excel sheet, where we shall write down the value of delta D from the first sheet. So delta D equal to, go to the first sheet, and delta D is here. I think it will work. Yes. ME equal to, ME also is required. ME equal to first sheet. M is this. Here it has got transferred, and J equivalent equal to from the first sheet. J equivalent calculated this. Then rest calculation needs to be done here. So you calculate the value of Ke. Ke equal to 4 pi square me divided t square. T we do not know till now. So we have to calculate T corresponding to the displacement spectra. This I have constructed for the Eurocode at 0.42 G seismicity level and various dampings. So our delta D value is 0.429. So delta D, you see here, 0.4 to 0.43 around. So 0.43, where it will be, you just put some line here. 0.5 is here, 0.43 will be somewhere here. Okay, and our damping was 11.7%. So you see, where is 11.7% here? This 5%, red is 10%, then this dotted is 13%. So 11.7%, there is almost near 12% will be somewhere here in between the red line and the dotted line. So this approximation you can make, or you can go back to your generation of the spectrum and exactly generate a line here for this 11.7% damping. Anyway, we shall make the approximation here. 11.7% is between the red line and the dotted black line. So we put another line here vertically downward from this point. I think 11.7 will be somewhere here at this juncture of this cutting of these two blue lines, and it is coming downward. So this is your effective time period. So effective time period here, it is coming around say 3.6 second. So TE is 0.6 second. Let us write down T is here. So it is 3.6 second T value. T value is here. Now we have to find the VB value. Before that I require to calculate Ke value, the effective stiffness. So this is equal to 4 pi square multiplied by ME, which is here, divided by T square. T is this. So I think it's all right. Yes, so this is the value of Ke. It will be coming in kilonewton per meter. I think visible nicely. Now we calculate BB. BB equal to, you remember what is BB? BB equal to Ke into delta D. Ke into delta D. So we calculate BB here equal to Ke star delta D here. So this much kilonewton. So this is your BB value. So the base shear we have now computed. For this base shear you have to design the building. Before designing, you have to distribute this base shear over the different floors. That distribution formula we have discussed yesterday. Means in the last slide, last video. When it is less than or equal to 10 story, so this is the distribution formula. So through this formula we can distribute the forces. So Mi delta I column and summation Mi delta I value we require. So we can take it out from the previous sheet. Mi delta I column is this. We copy this here and put it in the Mi delta I column of this second sheet. No, you have to paste not like this, undo it and paste special and you have to use formula, otherwise formula will not come here, then also it will not work. So let us do it like this. special values. Yeah, now you see values have come, and you don't record so many decimals, so we can reduce the decimals. Yes, then summation of mi delta I we can take from the previous column. We can put here equal to and go to the previous is summation mi delta I is here. So it has come. Now Fi is given by this formula, Bb into mi delta I divided summation mi delta I. Summation is here. So this is equal to your Bb we have calculated here, and since it is remaining constant, we have to put dollar star mi delta I, which is here, divided by summation mi delta I, which is this, and this is constant. Now you apply it over the other floors, and these are the forces distributed over the different floors. Forces will come in kilonewton. Sorry, forces will come in Newton, because we have taken in kg. So finally it will come in Newton. So it is it will be 202 kilonewton, like that. So force is in Newton. We can make a check here whether our calculation was correct. So equal to sum, if you take of all the forces that is distributed over the floors, how much it comes to? It comes to this 29,91014, which is here. It is equal to base shear. So our calculation is correct. Now these forces are to be applied in the model, in the computer model, at different floors. There are two ways of putting the forces in the model. One way is to put this force at the CG of the floor at the representative point. Another way is to divide this force into the number of the frames available and distribute over the frames these forces in the floors. Either way you will get the same result of the responses, and bending moment, shear, whatever, displacement, drift will come similar. So in future we may be taking up to the application of these things in the SAP model, SAP 2000 model. But I think up to here the application of the numerical part is clear to you. Thank you very much. Please subscribe the channel and share and like the videos. Put your comments and queries in the comment box. Thank you.